who's going to talk to us today and make a radiography on cosmology. Rogério, he got his PhD at the University of Chicago long ago, not so long. He was director here in IFT for 6 years. He was president of the Brazilian Society of Physics. He's vice director of the ICTP South American Institute for Fundamental Research, the ICTP-SAIFR. He's vice coordinator of the National Institute of the E-Universe. He's member of the LINEA, Interinstitutional Laboratory of E-Astronomy, and of DES. Wow. And he's also the vice director, and he's member of the Collaboration Rubin Observatory Legacy Survey, the LSST. And I think that's enough, right, Rogério? Okay, so thank you very much for accepting our invitation.
Thank you, George.
Please, go ahead.
So I start with a joke, because I remember once Rocky Cove was making an introduction of Mike Turner, and it went on and on, like you did, and then Mike Turner started his talk saying, well, in the remaining time, I will talk about challenges and opportunities in cosmology. That was something ordered by Jorge, and Jorge already said everything here, so I'm vice coordinator of this INCT, and part of LSST, of Rubin, of Dark Energy Survey, of the Dark Energy Science Collaboration of LSST. So this is a colloquium, so I'm going to start with a historical review about cosmology. I hope you forgive me for that. So let's start with a brief. Let's see the best moments of cosmology. Like in soccer, you have best moments. So let's start with the best moments of cosmology. Of course, this is all very personal. I didn't put personal in the title, but I think the original title had personal. So this is my personal best moments in cosmology. So for me, cosmology started really, modern cosmology started in 1917, when Einstein applied his general relativity theory that he finished in 2 years before to the whole universe. So this was the first paper, this is the first paper in modern cosmology, I think. This is modern cosmology. So in 1917, there was a paper of Einstein. Also, there were 3 papers by De Sitter, by the same year, which is amazing. So Einstein had a model which was static. So this is Einstein. And De Sitter. So Einstein had a model with matter, only matter, but then he found out that he wanted the model to be static, so those are static models. So Einstein had to introduce a cosmological constant to make it static. So this was the first time that the cosmological constant was introduced in physics. And De Sitter, so Einstein was dominated by matter, but had a cosmological constant. De Sitter only was dominated by cosmological constant. So the matter was insignificant. And it was a static model. So ask, what is Horacio? You should ask Horacio, how can you make a static model with a cosmological constant? But it was a static model. So this was 1917. 1922, Friedman, looking at the equations of GR, said, oh, why can't you why do you need a static universe? Universe can be expanding, contracting, etc. So this was 1922. 1927, I think there was another very important paper of Lemaitre, basically recovering the same equations that Friedman had discovered in 1922. So 1927, Lemaitre had the same equations, but Friedman was mostly a mathematician, so it was just the possibility, mathematical possibility. But Lemaitre actually looked at data at that time, and he found that the universe was expanding before Hubble. So now, you know the Hubble law, right? The Hubble law, the correct way is Hubble-Lemaître law. This was decided a couple of years ago in the Astronomical Union. Einstein was first. De Sitter knew about Einstein. And in fact, his model is an alternative to Einstein model. And so let me tell you something that's very interesting. So in 1929, of course, the paper of Hubble, and the expansion of the universe, right? The universe is not static, it's expanding. If you read the paper, there's no single word about expansion of the universe. He says that this can be an evidence of the quote-unquote De Sitter effect. So what was the De Sitter effect? This is why the De Sitter model where cosmological constant was static. How can you have a model with a cosmological constant being static? Because De Sitter used a coordinate system where time was changing and the space was static. So the frequency of light would change with time, with distance. And this is why Hubble never said that the universe was expanding, said maybe this is the Sitter effect. Doesn't matter, okay? This is just, everybody says that Hubble found the expansion of the universe. Okay, so then in the 1940s, late 1940s, the group of Gamov and collaborators, they proposed a model where the universe was initially hot and dense. So Big Bang cosmology started in the 48s. And the next best moment for me was when a prediction made by this group in, I don't know, 49 or 50, that the universe had a primordial temperature. Actually, they predicted 5 degrees Kelvin. And of course, it was totally luck that, that they predicted this value, because they had so many assumptions anyways. So in 1965, discovery of CMB. So 1970s, starting 1970s, even before a bit, the idea that you need dark matter. Talk a little bit more about that. And then in 1990s, there was precision studies of CMB. Started in 1990s. And of course, 1998. What happened in 1998, students? What happened in 1998? Yes, accelerated expansion. And then in 2000s, until today, is what we call the precision era of cosmology, with more and more precise measurements, which I'm going to talk about. So this is what I'm going to talk about. Let's see if I didn't forget anything. There was one important thing that didn't, yeah. Also in the 80s, there was one important development in the 80s. Maybe I should say here, in the 80s. The idea of inflation. So this has to be my list of best moments, right? Inflation was developed in 1980s. All right. Yeah, I also say here Big Bang. So and Big Bang. I talk a little bit more about Big Bang nucleosynthesis. All right. Let's see if I forgot anything. Okay. So precision cosmology. In the end, what happens is that there was an emergency of the standard model of cosmology. The same way that we have a standard model in particle physics, now we have a standard model in cosmology, and that's what we call lambda CDM. So it's a model which is based on a cosmological constant, lambda what? Sorry, thank you, Nathan. Thank you. Thank you. Thank you. So maybe it's my subconscious, right? So this is the standard model of cosmology, lambda CDM plus inflation. So I would say that modern cosmology today is based on 3 unexpected discoveries. What are the unexpected discoveries? That there's more matter than what we expected. And that's dark matter. So more matter than expected. That led to dark matter. The discovery that the universe is pretty much homogeneous and isotropic in the past. It's not homogeneous isotropic today, but in the past it is pretty much homogeneous and isotropic. How can you explain this? Inflation, that's the way to explain. This was, actually this was not, well, this was one of the motivations for inflation, and also the acceleration of the universe. Which led to the idea of what's called dark energy, and lambda is the simplest, the cosmological constant is the simplest example of dark energy. All right, so this is how modern cosmology came about, by 3 unexpected discoveries. So now I'm going to show a couple of slides, historical slides. There's one date, I forgot one date here. And this is really important. And this date is 1932. You know what happened in 1932? These 2 guys here, Einstein and de Sitter, who had proposed models totally different in 1917, they got together in Pasadena, and in one day they wrote a paper where they proposed a model, the simplest possible cosmological model. Say, the universe is expanding, why do I need a cosmological constant? Throw away the cosmological constant. There's no evidence that the universe has any curvature. Throw away curvature. So simplest model. No curvature, no cosmological constant, no curvature, so matter only. And this is called the Einstein-de Sitter model, EDS, not ADS, EDS, Einstein-de Sitter model. And this model became the standard model until the 90s, okay? So for me, this is a very important date. This has to be my best moments, which I forgot. Yes, yes. Yes. Yeah, it was singular, but people were like physicists, they didn't care about that. So the only thing they care about was, so George Gamow was really a practical person, said, okay, the universe in the past has to be hot enough, and if it's hot enough, what are the consequences? That's it. So they're not general relativists. They're not worried about singularities, as far as I know. Maybe Friedman was. Yeah, EDS was, Einstein de Sitter. Yeah. Flat. Yeah, spatially flat. Yeah, spatially flat. Yeah, spatially flat. So it's always spatially flat. So when we say a flat lambda CDM is spatially flat, Einstein de Sitter was spatially flat. Right. I was going to say another thing. Yeah, so Friedman thought about the singularity as 1922, right? His universe had singularities in the beginning, and he even tried to estimate the age of the universe, which was very interesting at that time. He got the usual 10 billion years, whatever. It was amazing. Okay, so this is I just have some pictures to show of some history, which I like history. So this is Einstein looking at the Palomar telescope. You know who this guy is, right? This is Hubble. This I'm not sure who he is, but this is Edwin Hubble. This is Einstein. Who knows? This is Millikan, Robert Millikan. He was the president of the Caltech. Nowadays, actually, his name is being removed because he was found to be what? You know this. He was found to be I don't remember, racist or something like that. Anyways, this is Millikan. Everybody suffered from the Millikan experiment when they were undergrads. I did. I suffered. Who knows who this guy is? This priest is Lemaitre. So Georges Lemaitre was a priest, an abbé in French, which, by the way, I don't know if there's a connection, but the word Abba in Hebrew is father. So abbé is father also in some ways. So I don't know if there's a connection. I have to think about that. And this is Einstein. And this, do you know who this guy is? De Sitter. So this is Einstein, De Sitter, 1932, writing their paper. And yeah, so this is the famous paper of that we're talking about lunch, right? The alpha, beta, gamma paper. The first paper about nucleosynthesis, Big Bang nucleosynthesis. The origin of chemical elements. This is 1948. And this is George Gamow and Hans Bethe, who was actually not in the paper. His name was in the paper, but he didn't participate in the paper. And Alpher. And this is how do you say montage? How do you say montage in English? How do you say montage in English, Nathan? Montagem. Photoshop? I don't know. Very old Photoshop. So this is actually Hermann and Alpher, and this is George Gamow coming out of a bottle of he called Elam. Elam was the primordial substance of the universe. So yeah. So about these best moments, of course, there were Nobel Prize involved. So in 1978, Penzias and Wilson, they shared the Nobel Prize for the discovery of the cosmic microwave background radiation. 2006, Matter and Smoot, they shared the Nobel Prize for the discovery of the black body form of the anisotropy, so fluctuations in the cosmic microwave background. Some people say fingerprints of God. Some other people say smallpox of God because it looked like smallpox. And then 2011 was the Nobel Prize for the discovery of the accelerating expansion of the universe through observations of distant supernova. So half went to Perlmutter, and the other half went to Brian Schmidt and Adam Rees. And the Nobel Prize of 2019 that was shared by James Peebles for theoretical discoveries in physical cosmology. So James Peebles really had an important role in putting the cosmology in very, very solid physics basis. And the other half was for something called exoplanets. Okay, they're important too. And also this guy, okay. All right, so what do I want to know? What do I want to say now? Okay, let's see if I want to say anything else before I continue. Right, so let me talk a little bit about the theory that we have. Don't have much of a theory. So how do we deal with this? What is the theory now behind cosmology? So the theory behind cosmology, at least the standard cosmological model, is general relativity. Plus particle physics. Plus, that's it. That's it, plus cosmology, but plus dark energy, plus inflation. Plus dark matter, because dark matter, let me call this standard model particle physics, and dark matter has to be something beyond the standard model. Okay, so of course Einstein's equation can be written in a content-free form, like this. Maybe there's an 8 pi g here. I don't care. So this is content-free, right? The only thing, this is Einstein tensor, this is the energy momentum tensor. So this is geometry, and this is particle physics. Yeah, that's what we have, plus cosmological constant if you want. So of course there are alternatives to this framework. So if you don't like GR and or you don't like cold dark matter, because those are the ingredients here, particle physics, there's no way. You have to, we know what they are there, but we don't know what dark matter is. We don't know what dark energy is. So we don't know if GR is correct. So if you want to go beyond this, be my guest. I just want to show you this because there are many alternatives to this framework. So if you don't like the simple cold dark matter model, there's many different types of of models for cold dark matter. Of course, I'm not going to go into this. And Otávio is here. Where is Otávio? Otávio is not here. So Otávio is working on axions, which is one type of dark matter. Pedro, another student of mine, is not here. He's doing some self-interacting dark matter. If you are not happy with general relativity, you can do many different things. And Isabella is working on some of these things, right? Sorry to put you on the spot, but it's right. So she's doing something of Horndeski, which is this thing here. So, all right, so we stick in this talk to the usual stuff. All right, so what do we do with this? So the easiest thing to do is to look at how average quantities in the universe evolve with time. So let me do this really quick for you. So we look at average quantities, like densities and pressures, etc. So so average quantities, take an average over certain certain volume. So and if you assume that the universe is on average, it obeys certain equations. So when I say average, I put a bar on top. The metric also has an average. And this average here is just the simplest possible thing that you can imagine. So the average quantities are only time dependent. They're not space dependent. This is the Friedman-Robertson-Lemaitre-Walker metric. So the metric depends only on one function, which is called the scale factor, which tells you how the universe expands. Okay, so if you plug this into Einstein's equation, this thing here, you get two equations. One is the two Friedman equations. Actually, Friedman was the first one to derive those equations in 1922. Now I put the 8 pi G3 again. So these are the two equations that governs the background universe. So once you put an equation of state relating density, pressure with density, and now I say, well, let me do something first. So let's say that the whole density is just a sum of different components of the universe, and this can be radiation, matter, and anything you want. And then using an equation of state that relates the pressure of some of these components to its energy density, so that's called the equation of state, you get exactly how the density varies with time. And this is one of my favorite plots. So I just want to show this plot. So this is log density. This is log time or log scale factor. This is today. So today, you have, I'm going to concentrate on three main components: radiation, matter, and the cosmological constant. Those are the three main ingredients. So today, radiation is very, very small. I put it here. Matter is somewhere around here, and the dominant part is the cosmological constant because we are accelerating now. So what happens is that the energy density of radiation grows with the fourth power. The energy density of matter goes like the third power, and you know what happens to the energy density of dark energy? It's just a constant. Sorry, this is supposed to be a constant. Okay. And this is much easier to draw because it corrects you, right? You put all right. So this is radiation. This is matter. And this is cosmological constant. So what happens in the past? So this is the past. Which component is dominant? Radiation. That means the universe is very hot and dense in the past. As all of you know by watching Big Bang Theory, because our whole universe started in a hot, dense state. That's the song, no? Sorry? No, there's no triple point. This is there's no triple point here either. But all right, so that's the background. So that's easy. That's the easy part, right? Right. So sorry, matter dominates at some point. That's important. Thank you, Ricardo. All right. So that's easy. Everybody knows how to do that. The question is, what happens when you have perturbations? Perturbations are not so easy. And how do you study perturbations? So get Einstein's equation, right? You see Einstein's equation there. So what's perturbations? It's this. As simple as that, where delta is a perturbation. So just you expand things, you expand the densities, for instance, as the average density plus some perturbations. And also the same thing with pressure, the same thing with metric. Same thing, okay? So one important quantity is, of course, what is the relation between the perturbation to the average perturbation, to the average density, and this is called delta, and this is very important, it's called density contrast. And yeah, I just want to say that when you do the perturbations in the metric, you have scalar perturbations, vector perturbations, and tensor perturbations. The scalar perturbations, they help the scalar perturbations in matter to grow, and the vector perturbations die, and the tensor perturbations are something that Ricardo likes, called, what's it called? Gravitational waves. Okay. Right, so the omega i's, if you look at non-relativistic matter, the mass is, the pressure is negligible compared to the mass. So omega I is 0. So we call this dust. If you look for relativistic particles, everyone that has taken a statistical mechanics course and has studied a relativistic gas will probably remember that the relation between pressure and energy density is 1/3. So that's 1/3. For the cosmological constant, you can show that's -1. Yes. Okay. All right. So that's right. So what we're interested is actually to see how these things grow, because these small fluctuations, they're small in the beginning, but they grow and they form galaxies eventually. And this is a very complicated nonlinear process. You can actually study the linear evolution, that's not difficult. But the nonlinear evolution is very difficult. And in fact, if this works, let's see if this will work. This will not work, right? So this is supposed to be a simulation. Okay. Should I do this or not? No. So this will, do you want to see this? Okay. It's somewhere here. Sorry. Huh? So this is very quick, because this is starting just some very, very uniform distribution of matter, and then let it evolve through gravity, and you get these very nice filaments and structures that actually not very different from what we observe. So let me go back. Ah, there was a button here. Yeah, this is Newtonian simulation. At this scales, you can use Newtonian gravity. Right, you see, yes, there's small fluctuations and you can predict. And in fact, maybe this next slide. What I'm doing here? Ah, now it works. I see. Okay. So this slide is just to show that you start with very small perturbations of the order 1 in 100,000. So this delta is like a 10 to the minus 5. This delta I just wrote, and then with time this grows and forms galaxies. This delta today is huge, right? Can you? It's because you know what's the yes. Some quiz for the students. You know what is the average density of the universe today? It's like 5. It corresponds to 5 hydrogen atoms per cubic meter. So it's really, really small. What? It's just Newtonian gravity. So Newton. It should be. I haven't done that, but it should be.
So everything came from the initial boundary conditions?
Everything came from, there's some random fluctuations in the, you don't see that, but there are some random perturbations here.
I understand, but it looks like there's more structure after than before, right? But that's just a mirage.
It's just gravity working.
No, but since the thing is time reversal invariant, I could have started in the end, and you would claim that that's gravity working.
Well, it's like mixing.
Okay, but that's
yeah.
what I'm saying. So
this is called entropy.
Saying that gravity organizes things is misleading, I think.
If you mix milk and
no, but
coffee,
you're not using that. That's what I'm trying to say. It's not some entropy. You're saying you're starting with it. You understand what I'm saying right now? Gravity is not doing the ordering. It's something else.
I think gravity is doing the ordering, and because it's getting places that have a little bit more density and attracting more things to that place.
Okay. We can talk about it.
All right. Okay, so this is.
I think the question, the point is that in a simulation like that, since you have infinite precision, you go back to one initial condition. But if we look at the universe today with finite precision, then there's an infinite number of initial conditions that will lead to the same universe. And then you don't have this reversibility. Yeah.
This is the simplest possible simulation. Of course, now there are simulations with gas and dissipation. This is the simplest thing you can do, okay? There are huge simulations now, much more. I just want to illustrate, but there are huge simulations, including dissipative dynamics. So it's not only gravity that forms galaxies in the end. But I just want to show this because this is the simplest thing you can do. This is only dark matter, non-dissipation dark matter. So observations. So I talked about theory. Now I want to talk about observations. So what are the observables that we can use to probe the universe? There are basically 3 types. One is Big Bang nucleosynthesis. The other is the CMB, the cosmic microwave background. And the other is how galaxies are distributed in the universe, large-scale structures. So those are the observables that we can use, most of them. I show some plots, but one interesting thing is that they probe different times of the universe. So Big Bang nucleosynthesis is like 3 minutes. Everybody probably read the book of Weinberg, the first 3 minutes, I hope. This guy here is like 380,000 years. And this guy here is like billions of years. So they probe different times of the universe. And I think I have a few plots here. Let's see. So this is the history of the universe. And the interesting thing is that all this history from 3 minutes to today, basically, is consistent with a single model, lambda CDM. So here's BBN, Big Bang nucleosynthesis, like 100 seconds when the first atoms, the nuclei of helium, etc., are formed, the CMB, and large-scale structures, okay? All right. So I'm going to focus on large-scale structures from now on. But before that, I think I have a plot on BBN. So this is the this is results from Big Bang nucleosynthesis. And you can see here the fraction of helium in the universe, the mass fraction as a function of either the baryon density or what is the same, baryon to photon ratio, which is around 10 to the minus 9. You see here helium, and the yellow rectangle is the experimental value, which has a large uncertainty. In this guy here. And there's the deuterium, which has a very small uncertainty. You see, you barely see the line here of deuterium and lithium. There's also this huge uncertainties. And then this is the results from CMB. So you see 2 different probes, Big Bang nucleosynthesis and the cosmic microwave background, and they agree in the abundance of light elements. There's some people call this a lithium problem. I'm not really worried because there's a large uncertainty. But this is a big success of the standard cosmological model. And also, just talk to make Louis happy, talk a little bit about CMB. Just one slide, Louis, sorry. So there's a huge progress in the detection and study of the cosmic microwave background. Started, I think I mentioned my favorite moments of the universe. There's a satellite called COBE that worked from 89 to 93. This is the map. Then there's something called the microwave anisotropy probe, Wilkinson microwave anisotropy probe. And you see that's much better resolution. Finally, Planck, which got this amazing map of the fluctuations in the cosmic microwave background. In addition, there's the Atacama Cosmology Telescope, the South Pole Telescope, and the future Simons Observatory, and S4 that Louis is involved. Yes. 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 Boomerang. I know. You're going to talk about boomerang. So okay. Ricardo is talking about a previous experiments, balloon experiments, and he's mentioning boomerang because there were some Italians involved, but it was French, but French-Italian, no?
Omega baryon, and it was measured for the first time through the CMB with boomerang.
Right.
So he started the precision cosmology before WMAP.
Okay, maybe I have to rewrite my favorite moments. So this is the amazing.
It's often being overlooked in this historical.
I know. Sorry about that. There's boomerang. I think there's another balloon which I forgot the name. But so Brazilians actually work in balloon experiments. Smoot was working on balloon experiments. George Smoot before these satellites. I forgot to mention, since Ricardo, these are all. Maybe I did mention. These are all satellites. But ACT and SPT are on the ground. So this is the South Pole, and this is the the name says, right? The Atacama Cosmology Telescope and the South Pole Telescope. So these are in the ground. And the Simons Observatory is also going to be in Chile. And S4, I have no idea. Do you know where S4 is going to be? Okay. Nice. So these are interesting things to look at because there are things in the cosmic microwave background that we still have to find. I don't know if I said this somewhere. Maybe I didn't. Okay. There's some. Okay, this is the amazing results of the measurement of what is called the angular Paul spectrum for the temperature of the cosmic microwave background, and you see that the red dots are the data, and the green line is a fit to this lambda CDM model, which has only 6 parameters. And those are the parameters, these parameters here that are determined. Omega baryon, omega cold dark matter. This is related to the angular size of the horizon at decoupling. This is optical depth. This is the amplitude of perturbations, and this is the spectral index of perturbations. And that's why we call this precision cosmology, because the errors are pretty small. These are derived quantities in the bottom from the top ones. This is amazing, okay? So this is what I call precision cosmology. I mean, I just want to say that again, to give my age away, when I started studying cosmology, the age of the universe was given by an error in the exponent. It was 10 to the 9 plus or minus 1 in the exponent, years. And now look at the precisions. Of course, this is the right, but look at the precision of the age of the universe. So this is incredible. Of course, precision can bring trouble, and you maybe not heard of the Hubble tension. So the Hubble parameter, which is just A dot over A, I didn't say that, but this is the Hubble the Hubble parameter today is A dot over A. Here's A double dot. So there, you see that there are two colors here. One are measurements coming from the local distance ladder, so basically supernova. And the green one is from CMB, especially from Planck. So it started around 2000, and it finished because Planck finished taking data. So we don't have any more data on CMB until Louis start working again. No, sorry. And so there is a discrepancy of the order of 5 sigma, because you have why is this not working? You have very good precision. Why this is? So there's some 5 sigma. So maybe this is a hint of new physics, and João here has he led a paper on an alternative to the standard cosmological model, which introduces another component called early dark energy. And Diogo, who is here, we just finished a revised version of a paper that uses neutrinos coupled to this early dark energy to explain, well, actually we showed it doesn't work, but anyway, it doesn't matter. Okay, so now I'm going to concentrate on large-scale structure in the remaining time. So now I'm going to start my talk in 15 minutes, so I hope to finish. So we have 2 main types of galaxy surveys. So now I'm going to talk about galaxy surveys, so large-scale structure of the universe. That's what I want to focus on. So BBN and CMB, I'm not going to talk anymore. How do we make a survey of galaxies? How do we see galaxies in the universe? There are 2 ways of doing this. One is that you take the spectra of the galaxies. So you have to collect the light of each galaxy, pass through a spectrograph, and take the spectrum. This is very time consuming, but you have a very good measurement of the spectral lines, so you can measure the redshift of the galaxies with very good precision. But it's very time consuming. The other method is using what's called taking pictures, like really a camera, like a camera of your cell phone. With it's a digital picture with filters, 5 or 6 filters. So you take pictures of a whole field and just see the galaxies that are there. So the idea with the filter is that the filter is a poor spectrograph. So you have a redshift that's not very well determined. We call this photometric redshift. But you have a huge number of objects, and you actually have pictures of the objects. So you can also not only see where the objects are, but you can also have an idea how the shapes are. And the shapes are distorted by weak gravitational lensing, for instance. Okay? So I'm going to mention the projects that I'm working on. So Dark Energy Survey and LSST, which are the second category of projects. They're photometric projects. Okay. And this is just a report on the, just for you to know what are the next experiments in the field. So we're going to talk about, so this is dark energy camera, this is Rubin. So dark energy survey stopped already, but the camera is still there. This is Rubin, this is the dark energy spectroscopic instrument, which is spectroscopic, and there's CMB, LIGO, etc., 21 centimeters. So this is the evolution of these 2 types of surveys. Imaging, there's this long digital sky survey, which, by the way, just finished 1 year, 2 years ago, 20 years of running. And they have an incredible catalog of spectroscopic galaxies. And then there's something called the spectroscopic, dark energy spectroscopic instrument, DESI. Sorry, this is imaging. So this is DS, and this is Vera Rubin Observatory. This is Long Digital Sky Survey, the spectroscopy. This is DESI, and then there's a new spectroscopy facility that's being thought of. So let me mention briefly the Dark Energy Survey. It's an international collaboration. There's around 600 people, which we just finished. This is the a picture of the collaboration meeting in 2018, which was at Unicamp. And so 25 institutions, 7 countries, a digital camera with lots of megapixels, 570 megapixels, which was located in this dome here. So this is the Blanco telescope in here, and this is the camera on the focal plane of the telescope. So you take pictures in the CCDs, and then you can see the images of the pictures here. So the full survey was finished in 2019, was 5.5 years. It's a wide field survey, 5,000 square degrees, which is 1/8 of the whole sky, 5 bands. And we have positions and shapes of 100 million galaxies for year 3. 100 million galaxies. It's a lot of galaxies. But okay, so, and then what we want to do is to check whether we are compatible with the data from CMB experiments. So if you can explain everything from lambda CDM. So just say a few words about this, the 3rd year of data analysis. So we have finished but data taking, but we're still analyzing the whole data set. But the year 3 was finished, and we combined with external data is the most stringent constraints that we have so far. And we can test the 6-parameter model, which is a flat lambda CDM model. And also we test some extensions of these models. Okay, what is this? So Jorge asked me to talk about challenges. So this is just to show you how complex it is to get from the pixels, from the pictures to cosmology. So there's a whole amount, a huge amount of work that has been done in order to get from images, calibrate the redshift, take the samples, you have to use simulations, you have to build the catalogs, you have to compute the redshift distributions, you have to compute the covariance matrices, and then you have to measure all these correlation functions, analysis choices, until you get to the final result, which is something like this. We call this banana plots. So we get these banana plots. This is the end of the analysis. So what we'll present in 2 minutes is some results from 3 times 2-point correlation functions, which our group has contributed. So this is our group. Let me just go back a little bit, because I also want to show contributions to the baryon acoustic oscillation. So our group did the harmonic space analysis, and also the harmonic space analysis of some correlation functions that was done by our group. So this is the group. Actually, so I started with Fabien Lacasa. You know Fabien, right? So Fabien was a postdoc here, and then Nick was an undergrad student here. Marcos Lima, Tonino Troia was a postdoc. Hugo is still a postdoc here, going to Brookhaven soon. Felipe was a postdoc here. He's at the University of Michigan, and Lucas Faga is a PhD student at IFUSP. So they all did some work and still working actually especially on the harmonic space analysis. So the observables that we use are the positions of the galaxies and the shapes of the galaxies. I think I have to go a little bit fast because I don't want to go over time. So we have galaxy distributions, and we want to measure correlation functions of shapes and of positions and mixed correlation functions. And here is the thing that also brings challenges, Jorge. So that's why how do we actually get to what we want to measure, the cosmological parameters? So this is like physics 101. Really. You have some data, you have some theory, and you have to compare data with theory. It's as simple as that. So you have some data, and this is the correlation functions that I just briefly mentioned before. So you have to have a theory, and from that theory, you have to model what you would expect the correlation functions to be as a function of parameters. So P is a set of parameters. Then you write down a likelihood function for this, how likely it is of the theory to describe the data, given some parameters. And then there's something called the covariance matrix that's really important. And then you sample the posterior distribution of the parameters to get the banana shapes. So now I'm going to talk about the challenges, because this is a thing. So there are challenges in modeling the correlation function. So what are the challenges? I told you that we're doing imaging surveys, so we use photometric, what's called photometric redshifts, and these have uncertainties, and we have to take into account these uncertainties when we make predictions. Also, something very important that maybe people don't realize is that in our models that we use, we don't put galaxies, we put dark matter and baryons. And dark matter and baryons have to form galaxies. So there's a relation between galaxies and the matter distribution, and it's called galaxy bias. And there are lots of developments on galaxy bias that are very recent developments. In fact, we had a candidate here for the position of Simons Papesp, Alexandre Barreiro, who is an expert on this theory of galaxy bias. There's the effect of intrinsic alignment of galaxies, that galaxies tend to align, and this masks the effect of gravitational lensing. There's calibration problems. There's this annoying fact that we exist. This is a very annoying fact, because we're baryons. So baryons are terrible because they affect, you have a supernova exploding that changes how galaxies form. So this is terrible. And also, gravity is nonlinear, and this is, we don't know how to compute nonlinear physics except by, putting the computer. So, so we have to take that into account as well. So those are challenges in the modeling, okay? And in fact, because we don't know how to model very well, we have to throw data away. We have just to throw data because we don't know how to model the data. So the issues in modeling, they are dealt with introducing some what's called nuisance parameters to parameterize uncertainties, and devising some scale cuts that leave out the data that we don't know. Okay, that's what it is. So this is Maria Gabriela. She was a student here, and she worked on mitigating some of these effects, so especially baryonic effects, with some theoretical error in the covariance. She went to University of Arizona after her master's, but I think she gave up physics. She's back in Brazil. And so there's some work in progress with Abdias. Is Abdias here? No, what are my students? João is here, Diogo is here, but where are my students? So Abdias is a master's student. Actually, he's going to work with Horacio. He got fed up with me, I suppose. So Abdias is working on mitigation of uncertainties in galaxy bias, together with Nick Cocron, who was an undergrad student here in Brazil, and he just finished his PhD at Stanford and is going to the Institute of Advanced Studies for a postdoc, and also with Felipe, who's a postdoc in Michigan. So we're right now working on this. So these are the cosmological parameters that we measure in dark energy survey. So there are 7 cosmological parameters and 30 nuisance parameters. So you can imagine what the problem is. So this is Andresa Campos. She was also a master's student here at IFT. She helped a lot in DS with this parameter estimation. Now she's probably finishing her PhD with Scott Doddleson. And now she's currently the year 6 weak lensing photo-Z coordinator. And so I like this because it shows what we have to do. This is a cartoon by Jesse Muir showing exactly those complicated steps in a cartoon. So we measure the light in the telescope. We have to separate galaxies from stars because we don't like stars, so we throw stars in the garbage. Don't tell this to an astrophysicist. Anyway, so there's a whole bunch until we get to these banana shapes. So I'm going to show some banana shapes. So these are banana shapes, and this is the typical. I'm not going to go into, sorry, I'm going to, okay. Just to show the type of constraints that we can get on the, this is the amplitude of clustering, and this is the density of matter. And these are the marginalized results. We also show that we're consistent with Planck, so we can combine the results and get the best results ever. Okay. So baryon-acoustic oscillations, our group helped in the harmonic space analysis. This is the real space analysis. This is separation in degrees, and this is the angular correlation function. So in terms of multipoles, so we analyzed these 2 things to get to this star here, which is the a 2.7 detection of the BAO feature. And then we have some papers led by Felipe Andrade Oliveira and Hugo Camacho, and here also Hugo Camacho. Hugo is not here. Nobody's here, because they already know this, of course. Anyways, they're working. Someone has to work, right? Okay, so these are some papers that we led in the dark energy survey. So I don't want to go into this. I don't want to go. Okay, so now we are going towards a full 3 times 2 point analysis harmonic space. So what about new physics? So when you have extensions like W0, W8, it's an extension of the lambda CDM with an extra parameter here, or 2 extra parameters, in fact. And Otávio Alves was also a master's student here at the institute at IFT. He helped a lot in this project, working with importance sampling for the extension papers. And he's now a PhD student at University of Michigan, working with Dragan Hutter, who is okay. So also, what about new physics? There's some work, I think I already mentioned that, but there's some work in progress. Actually, we finished this work. So this is an old slide with João here. And João is also working on emulators for COLA. And Diogo, he worked on neutrino early dark energy, but he's now interested in other things as well. And we are collaborating with Vivian Miranda, who is a professor at Stony Brook on this type of projects. So in the last, I have 3 minutes, if I remember correctly, because I started 3 minutes late. So I'm going to talk about the next state-of-the-art photometric survey, and that's the Legacy Server Space and Time, LSST. So what is the LSST? It's a 10-year project, a survey, to be conducted at the Rubin Observatory in Chile, using a telescope, 8.4 meters, brand new telescope, with almost 10 square degrees field of view, with the largest digital camera ever built, 3.2 gigapixels. So construction started in 2015, and the first light is next year, 2024. So I'm not going to this. There's a science book that you can read all about it. And there's, the LSST is organized into science collaborations. There are 8 of them. Those are, because this LSST is not only about dark energy. There are lots of things that can be done with LSST. So stars, Milky Way, local volume, solar system. By the way, do you know that the largest comet ever found was found using the dark energy survey by a Brazilian called Pedro Bernardinelli? So you should know this. So even dark energy survey is not all about dark energy. There's things that can be done. So yeah, so there are lots of stuff. And I'm working, of course, on dark energy. So I'm working the dark energy collaboration. So the LSST, this is the propaganda part. There's the Brazilian participation group. So I'm the current coordinator, and Thaisa is the vice coordinator. Tássia Ferreira is the spokesperson. And we have 10 PIs, original PIs, and this is the Linea that is a collaboration between Linea. The MOA was signed by Linea, someone from FAPESP, the LNA and RNP, doesn't matter. We have an additional 15 PIs from an in-kind contribution that were selected through a public call, and results were announced in July 2022. Ricardo is very angry at me because he didn't get in. And so at the moment, we have 23 PIs, etc. Argentina, Mexico just joined LSST, and of course, Chile is a native member. So more challenges and opportunities here. And so this is the Dark Energy Science Collaboration. There's more than 1,000 members already. So we want to learn about dark energy, again, using a combination of distribution of galaxies, distribution of shapes of galaxies, supernova, who is going to be, as we heard from Miguel, revolutionary, and cluster counts. And then combinations with external data, for instance, CMB, and that's where Louis should be helpful, very helpful to us, and gravitational waves also, etc. Right? So we have to combine this data. All right, so Tássia, this is just to show you that there are lots of working groups. We don't have data yet. It starts next year, but we're already working like crazy because we have to have all the pipelines ready when data comes. Okay, so I think I will stop here. So conclusions. So the Rubin Observatory's LSST will provide an unprecedented amount of data. There's an extremely rich science program with LSST, data that's ahead of us. And there are amazing opportunities that come together with several challenges, both experimental and theoretical, because we need to understand our data. So we need to model much better the data, because right now, as I said, we're throwing away data because we don't model them very well. So LSST 8 science collaborations are already in full action with data challenges, data preview, catalogs to test, model, the pipelines. So we're getting ready for the real data. The Brazilian participation group is already engaged in several of these science collaborations. Many of us have experience working already in something very similar. So the Dark Energy Survey was very similar to the LSST. I should say also in the conclusions that we are still finishing the analysis of the whole data set of dark energy survey. So the year 6 is finishing. I think early next year we have all the results from the year 6. And it's an amazing opportunity for students actually, because there's data and we can use the data and get bounds on whatever you want to, whatever model you want to test. So there was this recent expansion of BPG within in-kind contributions. So yeah, there's exciting times ahead, and we are eagerly waiting for the first light of LSST in 2024. So thank you, George. Thank you all. Sorry, it was a bit rushed.
Thank you very much, Rogério. Very illuminating. So questions?
There's lots of dark stuff here, no dark energy, dark matter, so it's good to throw some light on these things.
So how important is the matter, the choice of matter in these models, in these simulations?
The choice of matter.
Yeah, so the simulations are supposed to be real life, right?
Yes.
So how relevant is
so what
the
do you mean
choice
by matter? Just try to understand. By matter, you mean baryonic matter or dark matter or
What's
all
the
matter?
difference for the simulation? How does it know? You told me the W is the same, omega is the same for dark matter, and so how does it care if it's dark matter
So
or
if it's
baryonic?
if it's baryon, it has electromagnetic interactions, so it can dissipate. And the simulations are so developed for baryon matter, baryonic matter. The simulations are so developed that they can see the formation of stars and stars exploding, and that affects the formation of structures in the universe.
Okay, so things which are charged under QED. So that's the only thing that's
No.
relevant.
Also, this is baryonic matter. So dark matter also changes the formation of structure. For instance, do you know why I say cold dark matter and not hot dark matter? So hot dark matter, they're relativistic through the times when galaxies are forming. So any perturbations in dark matter will dissipate away because they're relativistic. That means that the power spectrum is suppressed when you have relativistic dark matter.
So that's the choice of omega, is that what you're saying?
And that's why hot dark matter is ruled out.
So is that just the choice of omega? I'm just
Yeah,
trying.
yeah.
So there is a choice you can make in the omega. It's not just zero.
Yeah, but there's some more details there too, because you can have self-interacting dark matter, and then you don't model by this. So this is, first of all, this omega is in the background. In the perturbations, it's much more complicated. You have speed of sound because perturbations propagate. So it's not only omega.
And if you change the number of neutrinos, does that change the simulation too, or no?
Yeah,
Okay,
if you put
so
more
all these
neutrinos,
things-
it changes. If you
Okay.
put more dark energy, it changes, yes. Yeah. So that's when so I'm old enough to remember the time where hot dark matter was considered. You probably remember that too, because you're as old as me. So, but hot dark matter was ruled out because they just don't agree with data. They dissipate the perturbations. So neutrinos are dark matter, right? But they're not cold dark matter. And that's how you put bounds on the mass of neutrinos. Yeah.
In fact, I think even the simulation you have shown needs some dissipation. Otherwise, how do those particles go down and stop there? You have to turn the gravitational energy into heat.
Yes.
And
It's not
otherwise
heat.
you don't get this stationary thing
Yes,
at the
some
end, right?
particles escape. I think that's the answer.
So you're losing information anyway,
Yeah,
right?
I think so.
Otherwise you don't get that,
Yeah.
right? They would just go
Yes.
through and spread
Yes.
all over the box.
So this is interesting. There's something called dynamical friction, which is exactly this. Only with gravity you have some friction because of gravity.
Yeah.
So only with gravity, which is amazing. Yeah.
I have a question.
Yes.
You told about the discrepancy in the Hubble constant when we evaluate it using CMB and supernova.
Yes.
But I know, and you said something about 5 sigma, right?
Yes.
But now there are some other data with red giants, which are in between.
Yes.
So what's your opinion? What's the status of this
so
situation?
the tip of red giants is still, where is it? The tip, so So what George is saying is that now, more recently, there's a new technique, which is not, well, it's a local measure, because it's stars.
Yeah.
It's called the tip of the red, how's it called? Tip of red branch giant, red giant branch, red. Tip of the red giant branch. So it's something about star evolution, and when the stars, there's a diagram that describes how stars evolve. And for red giants, there's a maximum luminosity, so people look at this maximum tip there, because you need a standard candle. Right. That's what you need. So this is a new method, and the calibration is still not... Supernovas have been here for more than 20 years now, so and people are being very careful with calibration of supernova using Cepheids from Hubble Space Telescope, etc., right? Now, I'm not following this very closely, but I think the uncertainties are still large. So it's in the middle, yes, but the uncertainties are very large. So the whole game here is about precision. How precise can you be? You see, there was no problem here. Why there was no problem here? Because, error bars were huge. Now precision. Now the error bars are
There's some drift in the central value.
Yeah, there's some drift. So maybe this is the calibration of supernova. No, this is CMB. So CMB. I'm not sure what the drift is in CMB. Maybe Louis knows.
And also,
oh, this is Planck. Yes, you're right. So Planck. So this is before Planck. This is after Planck.
I see.
Thank you, Louis. Yes.
And maybe Ricardo may answer this question. So I know that gravitational waves are going to shed some light when you have enough statistics with neutron stars. How long shall we wait for this?
Yeah, it's unlikely that the second generation of detector will shrink the error enough.
Sorry, unlikely or likely?
It's unlikely.
Unlikely.
So second generation detector will take data for 1.5 years from now, and then with the 2-year gaps for 2 additional years. But it's unlikely that the error will shrink enough to be competitive with this. So more likely we have to wait for a third generation detector in the 30s, in 2030s.
Okay, I think I will get it. I will reach it. Anyway, and what's your take about this discrepancy?
I'm agnostic. Of course, I would like to have new physics. And the people that are doing the supernova measurements are very careful. This is Adam Rees that's leading this for a long time. Other people outside have also been looking to find if there are any systematic uncertainties that are not accounted for. So far, people have not found any systematic uncertainties. The CMB data is very solid, but it's indirect. So it has you're not measuring directly the expansion of the universe. So there are some assumptions on how to translate. For instance, what they really have a good measurement is the angular size of what's called the acoustic horizon at the coupling. So that they have data, and it's very precise. Now, what happens when the light comes from there to us, that we don't know yet. So there's a possibility that João and Diogo are working on, where we have another component of the universe called early dark energy, which contributes around 10% of the energy budget of the universe around this time where CMB is produced. But then it decays away fast.
I see.
So you don't see it today. And there are models for that. And yeah, let me step back a little bit to say that there, of course, theorists love this type of things because they can put new models. So there are, I don't know, hundreds of new models that try to address this issue. But I think it's fair to say that early dark energy is one of the best models that were proposed. Best, I don't want to say the word best, but...
Thank you. I would say among the current proposed models, it's one of the most promising, but even early dark energy has its limitations. So people have very strong arguments and very strong feelings against early dark energy as well, even though it has been shown the Atacama Space Telescope data really favors the presence and the detection of early dark energy. but still people are skeptical about this kind of things.
Yeah. So I think the jury is still out. But again, no, we are physicists. So we have to wait for more data and see if there's a model that's compelling enough for us to really think, okay, this is it. We don't have that yet.
Okay.
But I think my take is that the data seems very solid to me.
Okay. Other questions?
Thanks. Just to be complete about the measurement of H0, there is also another way, which is to use this time delay cosmography, where you look at strong lensing,
Okay.
a system that has multiple images, and you have like an object, like a quasar in the background that is emitting at some specific frequency or something like that, and then you look at a different image and you can measure the variation of time.
Yes.
But you need to model very precisely the length, because you need to model precisely the path. So I think the error bars are still large, but maybe in the future with several systems you will get another measurement, independent measurement of H0.
What's the name of that supernova that has multiple images at different times? Repstal or something?
Yeah, I don't know.
You know what supernova I'm talking about, right?
Maybe, but I'm not sure.
Okay.
And I also wanted to make an advertisement for the Euclid telescope, because you didn't speak about it.
I forgot about the Euclid, sorry.
Which is also a photometric survey, and it will be launched in July, so in a few weeks now.
So there's a plot that I showed about future experiments, but I forgot to say that plot was done by DOE. No, experiments that are funded by DOE. So of course Euclid is European, so it was not in that plot. So thank you, Louis. Yes, Euclid will be also very, very important. And there was a problem the launching, because they were going to use the Soyuz spaceship before the war, and now it's SpaceX, I think. No.
Yes, exactly.
So it's July. So pay attention to this.
So I want to ask about your personal opinion on how promising you think it is to do the same kind of statistics that we do with galaxies, but with other kinds of objects that for now maybe we don't have enough, but as Miguel said the other day, we will have a bunch more supernovae in the future, and to use it not just to measure H0, but to measure the full lambda CDM model with the same statistics of galaxies. And further, we have also a bunch of gravitational waves in the same direction. So you think it would be as promising as what we do with galaxies, or would never be as good as?
No, even with galaxies, you can have different galaxies. So I think the answer to your question, that my personal view is that multi-tracer, that's the more general way of rephrasing your question. Multi-tracers are very important in order to eliminate systematic errors and things like that. So multi-tracer is important. I think this will be a game changer.
But on the systematic side, not on the statistical side, will we have as good statistics with these other traces as we have with galaxies?
Probably not. No. Probably not. But they still can help. Anything helps, Even if it's not enough statistics, anything helps.
We have billions of galaxies, right? We can observe
different types, yes. Yes. So at SST we have billions of galaxies, yes.
Any other questions? So let's thank again Rogério for this wonderful talk.